Hello everyone, I'm Joel Lee,
And my name is Jaime Castro.
and we are here to present the BANSHE UAV project, the research efforts of a multidisciplinary research project consisting of aerospace, electrical and computer, and mechanical engineering students and faculty at Cal Poly Pomona. Our UAV project aims to replace aircraft structure with power storage and power generation structures to reduce weight and increase flight endurance. Solar panels will replace the upper wing, graphene supercapacitors will replace the lower wing, thermoelectric generators generate energy from the motor's heat, and wing vibrations will be converted into electrical energy. A robotic arm with computer vision will automate the production of the supercapacitors. The project has 5 phases of flight, with the first phase done. Due to the COVID-19 campus closures, phases 1 through 4 were postponed. These multi-phase flight tests aim to demonstrate feasibility and increased endurance of the flying battery concept. The thrust and power consumption at varying throttle positions was measured using a load cell and a power meter, respectively. The data was used to determine the requirements for the power management system, solar panel and thermoelectric generator power generation performance, supercapacitor storage capacity, and thrust available. 170 watts, 11.4 volts, 16 amps was needed for 100% throttle to produce 1.6 pounds of thrust. 18 solar cells were required. Here's a flight profile for phase 0 and all the other flights. Each flight consists of takeoff in orange, loitering in green, and landing in purple. The phase 0 test flight revealed an unsafe revisionary mode when the voltage dropped below 10.4 volts, causing a nosedive, as shown in this flight path. The mass properties of the UAV were measured so that these values would serve as inputs into AVL to simulate stability and control. The trifilar pendulum method was used for finding the original UAV's roll, pitch, and yaw moments of inertia, and this will be repeated for the new fiberglass wing. The original tapered wing broke, and the new rectangular fiberglass wing needed to be manufactured to fit the 18 solar cell requirement and allow for higher G maneuvers. The AVL program was used to determine that the rectangular wing should be placed at an 11.6 inches aft from the nose to achieve the same tapered wing's 6% static margin reported in AVL. The power generation pod dampens wing vibrations and in the process charges the UAV's battery. A full-scale aircraft would have these mechanisms located inside the wing rather than using separate pods that would cause high aerodynamic drag. The team is investigating power pods' capability to reduce wing vibration due to gusts and also extract usable energy. The power generation pod is mounted into the Cal Poly Pomona subsonic wind tunnel with a wind gust system to excite wing vibrations. The pod itself is designed with 2 inner halves shown in black and red, covered by an outer fairing shown in brown to ensure consistent aerodynamic properties. The black half contains a carbon fiber leaf spring mechanism with a motor coupled to a gear. This mechanism is engaged with the gear located on the other half of the pod, which spins the motors and generates electricity as the entire mechanism moves up and down. A ground vibration test simulated wing vibrations due to wind gusts. A frequency sweep was performed at discrete mounting angles, and the tests were required to optimize the orientation of the power pod system. These graphs show the maximum power and voltage generated at each pod angle at consistent frequency sweeps. As seen in the peaks of the 2 graphs, the greatest damping and power generation occurs when the power pod is oriented 30 degrees toward the wingtips.
Thank you, Joel. As my partner mentioned earlier, flexible solar cells will replace the wing upper skin structure and take in energy to output straight DC current to charge the systems. The bottom skin of the wing is meant to be comprised of graphene supercapacitors. Supercapacitors will be used to aid needed short bursts of power. Solar cells will charge the supercapacitor while also providing useful structure. The specific type of solar cells that were chosen were the C60 solar cells developed by SunPower. These cells are used on most UAV systems and were even measured to have an efficiency rating of 22.4%, 30 degrees of flexibility, along with 0.6 volts and 6 amps. In order to make a continuous structure out of the solar cells, the team adds metal bus bars to the cells as well as encasing them in a laminate. These cells are also tested for their tension strength using the Shimatsu tension tester. Feasibility of using the solar cells to replace the skin structure is currently being investigated. Earlier in the presentation, Joel had mentioned about our flight testing dates being in March and April. These months are great for the available sunlight that is available. This means more photons will hit the surface of the C60 solar cells. This time period is also optimal because it lands at the end of the school year when the team can experiment with all the optimizations that they worked on. The most effective BANSHE UAV operation time frame occurs in June. The supercapacitor subteam has been working on developing structurally sound supercapacitors to lay in an array to replace the lower wing skin of the UAV. These supercapacitors will be used to aid the UAV in performing quick maneuvers, such as readjusting its position. To accomplish this, the team uses stainless steel substrates, graphene sheets as the activated carbon, and electrolyte gel including phosphoric acid, Teflon as their dielectric. Sealing the supercapacitor is achieved by simply using different tapes, but the team is hoping to use a non-conductive adhesive. Supercapacitors must be designed to withstand a 625 psi tension stress from wing bending. To test our supercapacitors, we partnered with the University of California, Riverside, as they have a Versostat 4 potentiostat galvanostat. This machine allows us to test our supercapacitors with single as well as multiple cycles. The CV curves below were measured at different scan rates and they exhibit typical capacitive symmetry shapes along the center. Our current ranges from negative 0.1 to 0.1 milliamps when tested at a scan rate of 2 volts per second and a potential range from negative 1 to 1 volts. Testing demonstrates proof of concept but yields less than desired amperage and voltage storage capability. By utilizing a robotic arm and a computer vision system, the team can take advantage of the speed and precision of automated supercapacitor assembly. This team implements the program known as YOLO. This program is efficient as it only takes one look at the working area, identifies the parts, and then begins the process. The team is currently using a vacuum pump to pick up and stack the individual components. In the future, the team plans to run the arm off an NVIDIA Jetson TX2 and will figure out how to dispense the gel in a thin and uniform distribution. The team is currently investigating automation methods for manufacturing structural graphene supercaps. Thermoelectric generators operate as a pair of two conducting plates with one side which is heated and the other side kept cold. This difference in energy converts the temperature difference into voltage as the charge carriers move and diffuse away inside the semiconductor. In the end, the charge carriers build up and are proportional to the temperature difference across the plate. This charge builds up and creates the DC voltage potential, essentially extracting motor heat for power to charge the battery. The power management system will promote efficient use of all of the UAV's components. The power management system will mainly be powered by the C60 solar cells. The output of these cells will go through a buck boost converter that will serve as the bridge to charge the LiPo. The battery pack will serve as the main source of power for the motor alongside the ESC and receiver. A balance charger is implemented in order to provide reserve power from a battery pack in case the inputs fail. The system will also include relay boards instructed by an Arduino Nano for switching between the different current sources in the system.
In the near future, phases 1 through 3 flight testing will occur. To mitigate the risks that the COVID-19 shutdowns has placed on the project, there is more emphasis on ground testing that can be done at home, such as the 3 shown on this slide. Our vision of the flying battery concept is a work in progress, but shows promise to increase UAV endurance. Thank you, judges and event organizers, for providing us with an opportunity to share our research with a broader audience. If you would like to email us any questions, here's our contact information. We would like to thank the following advisors and sponsors, mainly Professor Stephen Dobbs and Dr. Jenny Yu. Scan this QR code to see more of our videos.